All right, today we are diving into something that is, and I'm not exaggerating, a revolutionary shift in how we understand the world. We're talking about a technology that's changing everything from engineering to climate science. This is all about AI that doesn't just learn from data, it actually learns the fundamental laws of physics.
Just think about that for a second. What if you could perfectly simulate reality? Not in months, not in weeks, but almost instantly. Now, this isn't some far-off science fiction anymore. It's the promise of a whole new kind of simulation. And believe me, it's already happening. But to really get why this is such a massive deal, we first need to understand the problem it's solving. You see, for decades, computer simulation has been a cornerstone of science and engineering. I mean, it's incredibly powerful. But we've been hitting a fundamental limit, something you could call the simulation wall. And that wall, it's really built on a huge trade-off. On one side, you've got your traditional physics simulations. They are precise, they are spot-on accurate, but man, are they painfully slow. And they need an insane amount of computing power. On the other side, you've got purely data-driven AI. It's blazing fast for sure, but it often gets the physics wrong, and it's not great at generalizing. It doesn't really understand the rules, So it can make some pretty big mistakes when it sees something new. So we've been stuck with this choice. Do you want it right, or do you want it right now? But what if you could have both? What if you could just smash right through that wall by creating an AI that was both fast and accurate? Well, the solution is to stop treating AI like a student who only memorizes answers for the test, and instead to actually teach it the textbook. And this is the core idea right here. It's called physics-informed machine learning. We're not just throwing mountains of data at an AI model anymore. We are embedding the fundamental laws of nature, the actual equations that govern our universe, directly into its learning process. So think of it this way. While the AI is training, if it makes a prediction that violates a law, like conservation of energy, the model gets penalized. This basically forces it to find solutions that aren't just statistically likely, but are physically possible. This fusion, this is the secret sauce. It's the magic ingredient. By combining the raw speed of AI with the unbreakable rules of physics, you get a model that learns from data but is always grounded in reality. It literally can't break the laws of physics because those laws are now part of its code. And this is how you get models that are both ridiculously fast and physically accurate. And the tool that's making all this possible for developers and scientists everywhere is NVIDIA's PhysicsNeMo. It's an open-source platform designed from the ground up to build these new physics-aware AI models. We call them AI surrogates. So how does this engine actually work? Let's pop the hood for a second and see what makes these AI surrogate models so brilliant. This analogy is just perfect. A traditional simulation is like a student who has to meticulously solve a complex problem step by step every single time. An AI surrogate model built with PhysicsNeMo, that's like the seasoned professor who's seen that problem 1,000 times before. They can just glance at it and, based on a deep understanding of the rules, give you the right answer almost instantly. It's not recalculating everything, it's emulating the outcome. Now, what's really cool is that PhysicsNeMo isn't just a single one-size-fits-all tool. Nope, it's a whole AI toolkit. It has different architectures for different kinds of physics problems. So, for example, you might use neural operators for stuff like fluid dynamics, while graph neural networks are amazing for modeling complex, messy systems like how molecules interact. This versatility is absolutely key. And getting started building one of these models is surprisingly straightforward. First, we start with the shape of your object, say a wind turbine blade. Then, you tell the model which laws of physics apply, the equations for fluid dynamics. And finally, you train that model at a massive scale, and boom, out comes an AI surrogate ready to make predictions in a tiny fraction of the time. Okay, so this all sounds great in theory, right? But the real-world impact, this is where things get truly mind-blowing. This technology is already starting revolutions in entire industries. Just let that number sink in for a moment. 100,000 times faster. This isn't just a small improvement, this is a complete paradigm shift. And here's what that kind of speed means in practice. Shell is using PhysicsNeMo to model underground CO2 storage. A process that once took months of heavy computation can now be screened almost instantly. This is dramatically accelerating the search for real solutions to fight climate change. And the crazy numbers just keep on coming. Let's look at another one, 10,000 times faster. So where is this 10,000 times speed up being used? In our energy grid.
Siemens Energy is using these AI surrogates to predict how critical grid components heat up. This lets them move from slow, offline analysis to near real-time monitoring, which helps create a more stable and resilient power grid for every single one of us.
And honestly, the list just goes on and on. Ansys is designing better computer chips with it. Siemens Gamesa is building more efficient wind farms. In medicine, researchers are creating personalized simulations of blood flow to plan better treatments. AXA is more accurately predicting hurricane risks. And BRI is creating AI that can predict devastating floods hours ahead of time. I mean, the applications are as vast as physics itself.
So, what's the big takeaway here? What does this all add up to? Well, we are stepping into an entirely new era of what is possible.
The really crucial point is that this isn't just about making old simulations faster. It's enabling something completely new, the real-time digital twin. Imagine a live, virtual copy of a jet engine, a power plant, or maybe even a human heart, constantly updated with real-world data and able to predict what's going to happen next, in an instant. That is the future that's being built right now. And this matters to every single one of us. It means new medicines and technologies get into our hands faster. It means products get cheaper and more reliable because they're perfected in the virtual world first. It gives us powerful new tools to go after the grand challenges, like climate change. And it means a safer world with much better predictions for extreme weather and natural disasters. Look, what this technology really does is hand us a kind of crystal ball, one that's grounded in the actual laws of physics. The ability to ask what if on a massive scale and get an immediate, accurate answer, that's like a superpower for humanity. So it leaves us with one final and very exciting question to think about. What problems are we going to solve next?